Hey there, math fans. The Earth is not a sphere, it's an oblate spheroid. Fun to say that. Many of you probably know that already, and I claim to be no expert, but I am a longtime calculus instructor. I've taught about 20,000 students. For years, I've taught them this thing called Clairaut's theorem about the mixed partial derivatives of a multivariable function being equal under certain conditions. And so I was looking up the history of Clairaut once again. I've looked it up before, but I dug a little deeper than usual. And so one of the first major things that Clairaut did, if you look up Clairaut's theorem, is a theorem about gravity. So it's not about this. So this video is not about something I actually know about, but I thought it was pretty interesting. So the history goes like this. In the 1600s, there was a notice that the gravity wasn't the same, like if you were at the North Pole or the equator. So I made a little model of this just to see, and it was found that it's about 5% greater at the poles. So it's kind of an interesting thing I'd never really thought about. Maybe others had thought about it. And I guess there's quite a bit about this, but this provided evidence that perhaps the Earth wasn't a perfect sphere. Okay, so I just been reading on this. This is the Wikipedia article. Now, as I thought about it, that does make a little bit of sense because those of you know a little bit about gravity. You have the gravitational constant, you have the mass of the two objects, and you have this inverse square law that says the further the things get away, the less the gravity takes effect. And so if you're closer, then maybe we would think, oh yeah, gravity should be more. You're closer here. And there's other effects. There's the fact that this person on the outer edge is spinning faster. Make it so you can see them better. Sorry about that. But there's also issues about how the mass distributed. But anyways, there's interesting history here that I thought, kind of starts around the time of calculus. So I thought it was worth grabbing onto. So anyways, there was some notice about this. And then what it says is that Newton talked about this. And he theorized that the Earth was not precisely a sphere, but an oblate ellipsoid. So he said, we don't know, maybe it's ellipsoid. Now, the reason it's the terminology, I'd never really heard this, but an oblate spheroid is actually the equator is a circle. So Newton was saying, I don't know if the equator is a circle. Let's assume it's an ellipsoid. Maybe it's an ellipse in all three directions, but flattened in some way this way. And I've exaggerated it in this picture. You can't really see it very well because it's a difference of, 25 kilometers, which is a lot, but not easy to see, especially when it's about over 6,300 kilometers. Okay, so then people wanted to study this. So interestingly, so that was the late 1600s. Interestingly, two prominent researchers took it on. And one was this French mathematician Clairaut. And they actually did an expedition to this very northern place to get a measure of the arc of the meridian, it says, and to try to get a sense of the eccentricity, which is how extreme the difference was. And they were able to say something about it. Okay? So I just thought that was sort of interesting because it's a precursor. This was before Clairaut first published about Clairaut's theorem about second partial. So it shows you some of the problems he was considering about surfaces. And also there was mention a little bit I read about studying orbits of the moon and the three-body problem. So he was doing these physics problems. So anyways, I think it said 1737. He published some work on this. I guess there was controversy because some of it maybe had some error, I don't know. And then controversy comparing it to Newton's, but Newton's was just a guess. It seems there was something going on. I don't know. But he had this formula, pretty accurate, based on the angle. All right. So I'm going to grab I grabbed several things here. So then, since then, this has been refined a little bit. Apologies for not. And I found a table somebody had posted online. Couldn't find a good reference. So this is not mine. But I found this of at the poles. This is the gravity at the poles and the gravity at the equator. And this is the sort of the best model, named after another scientist who sort of improved this. And it's about a 5% difference. But supposedly yes, the distance is the big factor. The fact that you're closer actually does make the gravity more near the equator. But the rotation has something to do with it, and I forget what this other term was. So anyways, I thought it was interesting in and of itself. I'd never heard that or thought about that. So then I made a little model here. And I made it do weird things like rotate. So there you go, rotating around. So supposedly, the person standing at the equator is moving much faster. That has a small effect on this. I tweaked the numbers. So right now it's extreme. The actual is more, now you can watch it kind of getting closer to what it actually looks like. It's pretty close to tweaking the numbers a little bit. Pretty close to this, which you can see you can't really tell much of what's going on there. The only other thing I did, I was just toying around with, look at that, toying around with colors and Desmos. So I drew a bunch of rings in there, and I unpacked the Earth. So anyways, you take an ellipse and you rotate it around this way, which means the radius, it is a circle from above. So that's the model that is used for the Earth, that from above it does indeed look like a circle, but from the side it's an ellipse. All right, thought that was an interesting little exploration. Clairaut's other theorem, some history, because this was about 3 years before. He then published more on this later, but it was 1740 that he published about things where it came up, this what's known as Clairaut's theorem in Calculus 3. All right, I found that interesting. Thanks for listening.